When we gaze at the vast night sky, filled with countless celestial bodies, it is difficult to imagine that our region of space might be particularly empty. Yet, growing evidence suggests that the Milky Way is situated in a vast cosmic void. While this may seem counterintuitive, it could actually be a stroke of luck, as our position in this gigantic empty region might help solve one of modern cosmology's greatest mysteries, the Hubble tension. The Hubble tension arises from a perplexing discrepancy between the predicted and observed expansion rates of the universe. According to theoretical models, the cosmos should expand at approximately 67 kilometers per second per megaparsec. However, direct observations indicate a faster rate of 73 kilometers per second per megaparsec. This difference of around 20,000 kilometers per hour per megaparsec is a major challenge for astrophysicists, as it contradicts the predictions of the standard cosmological model. To grasp the significance of this anomaly, we must first understand the Hubble constant, the measure of the universe's expansion rate. Named after Edwin Hubble, the astronomer who first discovered the universe's expansion in the 1920s, this constant describes how quickly galaxies recede from one another over cosmic distances. Unlike everyday motion, the universe does not expand into pre-existing space, rather, space itself is stretching, carrying galaxies along with it. The Hubble constant is typically expressed in units of kilometers per second per megaparsec. A megaparsec corresponds to about 3.26 million light-years, while a single light-year spans approximately 9.46 trillion kilometers. In practical terms, this means that for every 3.26 million light-years of distance, the velocity of cosmic expansion increases by around 67 kilometers per second, at least according to theoretical models. However, when astronomers measure this value using direct observations of supernovae, gravitational lenses, variable stars, or red giants, they consistently find a value closer to 73 kilometers per second per megaparsec. This persistent discrepancy has led scientists to question whether past measurements contain systematic errors. To resolve this doubt, Nobel laureate Adam Rees and his team at Johns Hopkins University analyzed extensive data from the James Webb Space Telescope, JWST, over the past 2 years. They meticulously examined the distances of 16 supernovae, red giants, variable stars, and a special class of carbon-rich giant stars. The result? Instead of resolving the discrepancy, the JWST data confirmed the Hubble tension yet again. The most comprehensive analysis to date determined an expansion rate of 72.6 kilometers per second per megaparsec, essentially reaffirming previous findings. This suggests that measurement errors are unlikely to be responsible for the observed deviations. Adam Rees openly acknowledged that our understanding of the cosmos may be incomplete. Perhaps the standard cosmological model is missing a crucial component, such as an unknown force or particle that influenced cosmic expansion after the Big Bang. Some scientists speculate that dark energy, the enigmatic force believed to accelerate the universe's expansion, might have evolved over time. Others propose exotic solutions involving unknown particles, variations in electron masses, or large-scale magnetic fields. However, one particularly intriguing hypothesis suggests that the key to solving the Hubble tension lies in the very emptiness of our cosmic neighborhood. Despite the Milky Way's vast collection of stars, 100 billion within a 100,000 light-year diameter, our galaxy and its surroundings might reside within an enormous underdense region, or cosmic void. To understand this possibility, we must examine the large-scale structure of the universe. Stars and planets do not drift through space in isolation, they are organized into galaxies, which cluster together into galaxy groups, which in turn form superclusters. For a long time, scientists believed that these superclusters represented the largest coherent structures in the universe. However, large-scale surveys have revealed that superclusters are not randomly scattered but instead form a vast, web-like structure composed of immense filaments. These filaments span millions of light-years and enclose enormous, nearly matter-free voids. The distribution of matter in the universe is thus highly uneven, with galaxies and galaxy clusters forming along these cosmic filaments while enormous regions remain almost entirely devoid of matter. More recently, astronomers from the universities of Bonn and St. Andrews reinforced this finding. They likened our cosmic position to a bubble in a rising loaf of bread, where surrounding matter is denser, pulling galaxies toward the denser regions and causing the remaining galaxies within the void to appear as if they are expanding outward at an accelerated rate. This scenario could provide a simple explanation for the Hubble tension. If we reside in an unusually empty region of space, then the apparent expansion rate we measure would naturally be higher than expected. In fact, astronomers recently analyzed the velocities of distant galaxies 600 million light-years away and discovered that these galaxies are receding from us 4 times faster than standard cosmological models predict. If this void hypothesis is correct, it could mean a major revision of our current cosmological understanding. According to the Standard Model, such enormous underdense regions should not exist on large scales because matter should be evenly distributed throughout the universe. The existence of a massive void challenges the fundamental assumptions of modern physics, particularly Einstein's theory of general relativity. Albert Einstein's general relativity has been the foundation of our understanding of gravity for over a century. However, if the universe contains vast voids that should not exist according to these models, we may need to rethink the very nature of gravity itself. A growing number of scientists are exploring modified gravity theories as an alternative to dark energy and traditional cosmology. One such theory, known as modified Newtonian dynamics, (MOND), was introduced in 1983 by Israeli physicist Mordechai Milgram. MOND suggests that the behavior of gravity changes at extremely low accelerations, potentially explaining galaxy rotation curves without invoking dark matter. Interestingly, MOND also predicts the existence of large cosmic voids, something that the Standard Model does not. If gravity behaves differently than Einstein's equations predict on cosmic scales, then the observed discrepancies in the Hubble constant could be the result of these irregularities in matter distribution rather than a fundamental flaw in our cosmological models. If MOND or a similar alternative proves correct, the implications would be profound. It would mean that the universe has only one true expansion rate, and the observed discrepancies are due to local variations in matter density. However, this would require abandoning key aspects of Newtonian gravity and Einstein's general relativity, an enormous paradigm shift in physics. For now, the debate remains unresolved. While the existence of a vast cosmic void around the Milky Way could help explain the Hubble tension, it also raises deeper questions about the fundamental nature of gravity, the distribution of matter in the universe, and whether dark energy truly exists as we currently understand it. Future observations, particularly those from next-generation telescopes and deep space surveys, will be essential in determining whether we must revise our understanding of the cosmos or if an even more extraordinary explanation awaits discovery. If our Milky Way truly resides within an immense cosmic void, then the implications for modern cosmology could be revolutionary. This hypothesis challenges one of the fundamental assumptions of the Standard Model of cosmology, namely, that matter is uniformly distributed throughout the universe on large scales. According to the lambda-CDM model, lambda cold dark matter, the cosmos should exhibit a homogeneous and isotropic structure when viewed over vast distances. However, if we find ourselves in a region with a much lower than average matter density, this could mean our measurements of cosmic expansion are skewed due to local variations in gravitational influence. The idea of a local void influencing expansion measurements is not new, but until recently, it was considered unlikely because standard models predict only small fluctuations in matter distribution. However, if our region is underdense enough, it would mean that gravitational forces from denser surrounding regions are pulling galaxies outward at an increased rate, mimicking a faster cosmic expansion when measured from Earth. This phenomenon is sometimes called the Hubble bubble effect, which suggests that our cosmic neighborhood is expanding more rapidly than the universe as a whole. Another avenue of research involves quantum effects in the early universe. Some physicists speculate that unknown quantum interactions during the first moments after the Big Bang could have influenced the large-scale structure of spacetime itself. These effects might have left imprints on the cosmic microwave background radiation and the subsequent evolution of cosmic expansion, leading to the discrepancies we observe today. As next-generation telescopes such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission come online, they will provide more precise measurements of galaxy distributions and cosmic expansion. These observations will either confirm the existence of an immense cosmic void influencing our local measurements or point toward entirely new physics beyond our current theories. Either way, the resolution of the Hubble tension could mark a turning point in our understanding of the cosmos, one that may rewrite the very foundations of modern physics. The universe is full of mysteries, and our cosmic neighborhood might hold the key to solving one of its biggest puzzles. Like, subscribe, and stay tuned to Space Lab for more cosmic discoveries.